This is problem 16-8. A 250 kilogram slab of material is supported on an inclined rail by shoes A and B as shown in the figure below. If the kinetic coefficient of friction between the rail and the shoes is mu sub k equal to 0.2, determine the normal and frictional forces exerted by the rail on the shoes while the slab is moving along the rail. Okay, so they're using some terms here that I just want to make sure that we are up to speed on. So first is that kinetic coefficient of friction is definitely implying that this thing is sliding. Okay, so you got this mu sub k for kinetic coefficient of friction. Okay, and then they said determine the normal and frictional forces exerted by the rail. So the normal being the forces perpendicular to the rail, and then there's going to be some frictional forces on the shoes of the rail as well. Okay. Don't forget center of gravity location matters, and they give us an incline with a 3 and a 1, a rise and a run. So let's take a look at the math for this. All right, so we talked about a lot of our givens, but let's go ahead and write them down. One is that the mass of this slab is 250 kilograms. And then we talked about the kinetic coefficient of friction is 0.2, unitless. And then they want us to find the normal and frictional forces. So we could say that like there's the normal for A, the normal for B, and then the friction of A and the friction of B, because they want the both feet. All right. So what do we need to do? Well, let's draw the free body diagram. I'll draw at a slight angle, of course. And then there are basically these rails. So I don't know, like just understand that there's like a rail passing through. Let me go ahead and just kind of in green, like, okay, so it's sliding on the rail, right? Now, let's put the forces that we need. So our normal force of A, our normal force of B, our frictional force of A, frictional force of B, our weight, which comes from the center of gravity but points straight down. And then they gave us that 3 to 1 angle. So there's going to be some sort of angle theta here. Normally, we would always do some of the forces of the x, some of the force of the y. But sometimes slightly different labels can be more appropriate. If you have your axes with an x and a y like this, then your axes are oriented with the normal and the frictional forces, and only the weight is going to be in an angle. Another way to label this, and just so you know that sometimes the book and the examples will be doing this, is that this is the normal axis and this is the tangential axis. Okay, so just for practice, I'm going to do my forces in that way. So we're going to do some of the forces in the tangential direction, some of the forces in the normal direction, and then we're going to do the sum of the moments about the center of gravity. So the forces in the tangential are basically all of the horizontal forces that are parallel with the rail. So we're going to have the gravity that is at an angle. In other words, the tangential component of the weight. Okay, so let me add that we have an arrow here. That's the normal component of the weight, and we have the tangential component of the weight. All right, that puts us at the 250 kilograms times the acceleration due to gravity. And then that'll be sine theta. The theta is here. All right, and then the rest is going to be minus the friction at A and minus the friction at B, because they're both going in the left direction along the tangential axis. And then the mass times the acceleration, 250 kilograms times the acceleration in the tangential direction. All right, some of the forces in the normal. So we're going to have the normal force of A plus the normal force of B. And then the weight is going down, basically. So minus, and I'm going to try and be consistent with the colors, the 250 kilograms times the acceleration due to gravity, and then cosine theta. All right, now we do not expect the slab to go off of the rail. So the mass times the normal acceleration is going to be 0. Okay, finally, we're going to have the moments about the center of gravity. So for moments, we are going to need distances, and I didn't put my distances in the diagram. So they tell us that basically the normal force is 1 meter away horizontally in both directions, both normal forces. And then they give us a height to the center of gravity that's 1.3 meters. All right, so that means that the moment for the normal force for A, so the normal of A is actually times 1 meter, plus the normal for B is also times 1 meter, okay, plus 1.3 meters times the frictional force of A, plus 1.3 meters times the frictional force of B. And there will be no rotation, so 0. All right, but double check. We got the normal force of A is going clockwise, so negative. Normal force of B is going counterclockwise, so positive is good. The frictional force of A is going counterclockwise, so positive is good. And the frictional force of B is going counterclockwise, so positive is good. All right, so we have theta, the frictional forces, and the normal forces. There's actually 5 unknowns. Okay, so we only have 3 equations. What are we going to do? Well, we do know that frictional calculations have normal forces in them. So the friction of A is going to equal the normal of A times the coefficient of kinetic friction, which is 0.2. And then the friction of B is equal to the normal of B times the kinetic coefficient of friction. There's our 4th and 5th equation. We need, we have the tangential acceleration, 6 unknowns. So we do need one more equation, and that equation can be finding the angle theta. So theta is equal to the inverse tangent of 1 over 3, that rise and run ratio. That equals 18.4 degrees. Okay, now we have enough equations to solve for everything. So in the end, NA, the normal of A, is equal to 1466 newtons. The normal of B is equal to 861 newtons. The frictional force of A is equal to 293 newtons. The frictional force of B is equal to 172 newtons. And then the tangential acceleration is equal to 1.24 meters per second squared.